Okay, in this video we're going to review a little bit about what we talked about in class today. Okay, so recall we have this utility function. It looks like an intertemporal utility function that's made up of consumption in time period t and consumption in time period t plus 1. Okay, here's the intertemporal nature of this utility function. I have utility of consumption in time period t here plus beta, where beta is, you can consider beta a constant stochastic discount factor. So what I'm going to do here is I'm going to discount expected utility of consumption in t plus 1. Okay, so just think of beta as a discount factor that I apply to my expected utility of consumption in time period t plus 1. Okay, so this is my objective function. Next, I have two constraints. First, my first constraint is going to be that consumption in time period t is equal to some endowment minus the price times some investable asset omega. Okay, so ET here, this is some amount of capital or endowment that the individual has. Okay, PT, you can think of this if we're going to save our money in a particular asset like a stock or something, you can think of this as the price of the stock times the number of shares of that stock. So a good example in practice would be something simple like, say this individual has $1,000, so ET is 1,000. The price of an ETF that tracks the S&P 500 is going to be, say, $300 a share. And so that individual might buy 2 shares, so omega here would be 2 shares times the going price, which is 300. So of the $1,000, the individual is going to spend 600 on this investment and consume the rest. The second constraint is that consumption in time period t plus 1 is equal to an endowment in time period t plus 1 times xt plus 1 here is a random payoff. Note that it's not the profit, but a payoff that comes from an investable asset that we purchased in time period t. Okay, so this is the payoff to this investable asset omega. All right, you should note that this payoff, it's not the profit, could be thought of to be equal to the price in time period t plus 1 as well as the dividend that this particular asset pays in time period t plus 1. Okay, so what we're going to do is we're going to substitute the constraints, the first and second constraint, back into the objective function, then take the first order conditions of the objective function, set it equal to 0, and solve for the price. Okay, so here's my objective function. I'm going to simply take this constraint and substitute it in here, take this second constraint, substitute it in here, and then take the partial derivative of this utility function with respect to the investable asset omega. I'm going to use the chain rule to do this. I take the partial derivative with respect to omega. I pull out my negative pt times, now I'm not going to place a functional form on this utility function of consumption. I'm just going to say that it's negative pt times the marginal utility of consumption in time period t plus, let me pull the discount factor beta outside the expectation here, and as well as pull out the expected payoff or the payoff in time period t plus 1 times the marginal utility of consumption in time period t plus 1. So I've just used the chain rule here to take this partial derivative. I'm going to set it equal to 0. I'm maximizing my objective function, setting it equal to 0, and then solving for p. Of course, I'm going to add both sides by this product of the price in time period t times the marginal utility of consumption in time period t. Divide both sides by that marginal utility, and I get the price of the asset, the investable asset, is equal to this discount factor beta times the ratio of the marginal utility of consumption in time period t plus 1 over the marginal utility of consumption in time period t. Think about what that means. Okay, so this is telling me what my marginal utility of consumption is in t plus 1 relative to my marginal utility of consumption in time period t. If I would rather or prefer to consume stuff today rather than tomorrow, then this ratio will be low. And my discount factor, which is multiplied by this low ratio, I'm going to lower my discount factor. Right? I'm going to discount the expected payoff of the investable asset at a lower level. Okay, so intuitively, hopefully that makes sense. All right. So recall that xt plus 1 is equal to the price of the investable asset in time period t plus 1 plus the dividend in time period t plus 1. Okay, I'm going to just substitute this fact into my price equation and look at what I have now. I have the price of the asset in time period t is equal to this discount factor, which is beta times the ratio of my marginal utilities times the expectation of the price in time period t plus 1 plus d plus 1. Now follow me down this slope here. I don't know what the price is going to be in time period t plus 1, but I do know, according to my formula here, that the price in time period t plus 1 is just going to be equal to my discount factor times my marginal utility ratio times the expectation of the price in t plus 2 plus the dividend in t plus 2. I don't know what the price in t plus 2 is, but I do know that the price in t plus 2 is going to be some function of this discount factor times the expected price in t plus 3 plus the dividend in t plus 3, and so on all the way to the kth time period. Okay? What I'm now going to do is I'm going to substitute this formula, the price in time period t plus 1, into my original price formula. I'm going to substitute this price in time period t plus 2 into this previous formula and do this recursive method until I get the following. The price of the asset in time period t is equal to the expected dividend to be paid in time period t plus 1, and I'm going to let my discount factor equal 1 over 1 plus r. And as I do this, I generate this general discount model that we've been using in finance since you've taken an introductory class. That is that the price of the asset is equal to the discounted dividend in time period t plus 1, where I discount it by 1 over 1 plus r, where r you can think of as being the required return by shareholders, plus the expected dividend in time period t plus 2 divided by 1 plus r raised to the power of 2, and so on. The expected dividend plus the expected dividend in time period 3 divided by 1 plus r raised to the power of 3, all the way to the kth time period, the expected dividend in time period t plus k, discounted back k periods by some rate r, plus the expected price of the stock in the kth time period, discounted back k time periods by some level r. Okay. Now you'll recall maybe from your introductory finance class that the price of the asset in time period t, which is equal to this discount model, I can make two simplifying assumptions. First, I can assume that dividends are going to grow at a constant rate of g, whatever g is, and they're going to grow at that rate indefinitely. And then I'm going to assume that the required return by shareholders is greater than g. And under these two assumptions, my discount model can be shown to simplify to this model, which is the general growth model that we've been using in finance, which is that the price of the asset in time period t is equal to the expected dividend to be paid out next period divided by r minus g. So here, under the assumption that the utility of an individual, the intertemporal utility of an individual, is some function of the consumption today and the discounted expected utility of consumption in the next period, can ultimately be shown to equal our general discount model that we've been using in finance since the intro class, and under these two simplifying assumptions, the growth model that we've been using.